Right now, while you're listening to this, something ancient and man-made is drifting through a place no human being has ever seen with their own eyes. It is tiny, it is cold, it should be moving through quiet emptiness by now, but it is not. It is crossing a region that keeps changing shape, sending back clues that do not fit the simple picture scientists once trusted. And what that hidden place is doing may change how we understand the shield around Earth itself. This is the hidden story of Voyager 1. Welcome back to Proof, where we uncover the hidden truths of the cosmos. If you are new here, hit subscribe now, because what you're about to hear is one of those stories that sounds impossible until the data start speaking. Voyager 1 is so far away that its signal needs almost a full day to crawl back to us. Think about that for a second. A message leaves that spacecraft, crosses the black between the stars, reaches giant radio dishes on Earth, and only then do we learn what touched it out there. That alone would make this story incredible. But that is not even the strangest part. Because the place Voyager 1 is moving through right now is supposed to become simple, calm, predictable. That was the old idea. Leave the sun behind, cross the edge of its giant bubble, drift farther out, then finally enter a more normal stretch of interstellar space, the space between stars where things should settle down. Instead, the farther Voyager went, the weirder the story became. And before we go deeper, drop a comment right now and tell me where you are watching from. I always love seeing how many corners of Earth gather for stories like this. To understand why this matters, we have to go back to the beginning. Voyager 1 launched on September 5th, 1977. That date feels almost unreal now. Bell-bottoms, tape players, no internet, no home computers like the ones you know, and yet a machine built in that world is still whispering to us from beyond the planets. At first, Voyager 1 was never meant for this kind of ending. It had a big job, but not this big. It was sent to visit the giant planets, Jupiter first, then Saturn. It flew past Jupiter in 1979 and showed us storms, moons, and a world more violent than most people imagined. Then it rushed past Saturn in 1980 and revealed new details about rings and moons that still shape science today. Most missions would have ended there in spirit, even if the spacecraft kept going. Voyager 1 did not end. It kept moving outward, year after year, past the bright family of planets, past the region where the sun rules with light and wind and magnetic force, toward a frontier people talked about for decades but had never touched. That frontier has a name, the heliopause. The heliopause is the outer border of the heliosphere. The heliosphere is the huge bubble made by the solar wind. The solar wind is a stream of charged particles flowing out from the sun in all directions. It pushes outward into the galaxy and helps create a protective bubble around our solar system. That bubble matters more than most people realize. It is not just a neat science fact. It helps shield the inner solar system from part of the radiation that comes from deeper space. Not all of it, not perfectly, but it matters. The shape of that shield helps decide what kind of energetic particles can reach the worlds inside, including Earth. So when Voyager 1 reached the edge of that bubble, this was not only a story about a lonely spacecraft, it was a story about the border of our home. On August 25th, 2012, Voyager 1 crossed the heliopause at about 121.6 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, so Voyager was more than 120 times farther from the Sun than Earth is. That crossing made history. Voyager 1 became the first human-made object to enter interstellar space, or at least that is the sentence you usually hear. And here is where the hidden story begins. Because even after that famous crossing, scientists did not step back and say, "Mystery solved." They looked at the data and started arguing. Not because the crossing never happened, but because the place just outside the heliopause did not behave the way the clean textbook picture said it should. For a long time, the simple version looked like this. The heliosphere was imagined like a smooth bubble or a comet shape, rounded in front, stretched into a long tail behind. The heliopause was treated like a fairly clear boundary. Cross it, and eventually you should move into a quieter, more uniform interstellar medium. The interstellar medium is the gas, dust, and plasma between stars. Plasma is a gas so energized that electrons break free from atoms, leaving a soup of charged particles. That old picture was useful. It was also incomplete. Voyager 1 started proving that almost immediately. The first twist was the boundary itself. Scientists expected a crossing. They got one. But not in the tidy way many models suggested. The change in particles was dramatic. The magnetic field changed. But the whole thing looked less like stepping through a door and more like moving through a complicated border zone. Layers, disturbances, features stacked on features. In other words, the edge of our solar system was not a wall. It was more like a living membrane. That matters because membranes can pass things through: pressure, energy, disturbances, information written into motion. So Voyager 1 did not leave the sun behind as completely as people hoped. In fact, one of the biggest surprises of the entire mission is that the sun kept reaching farther than expected. Years after the heliopause crossing, Voyager 1 was still detecting the effects of solar activity. Big eruptions from the sun can launch waves of pressure outward. When those disturbances travel through the heliosphere and hit the heliopause, some of that energy can keep moving into the interstellar medium beyond. Think about that. Our star can burp, flare, and throw out violent pulses. Those pulses race outward for years. Then, far beyond Pluto, far beyond the boundary where many people imagine the sun is done, those disturbances keep going. They shake the medium on the outside. That means the space around our solar system is not separated from us in the clean way people once pictured. It is connected. That connection showed up in shocks and pressure fronts that Voyager 1 detected after entering interstellar space. A shock is a sudden compression wave, like a sharp slam moving through a medium. A pressure front is a broader compression, more gradual in shape, but still a sign that something is pushing through. Voyager 1 saw multiple such events. This alone should have changed the way more people talk about interstellar space near our system. Because empty space was not empty. Quiet space was not quiet. It had structure. It had motion. It had weather of a sort. And then everything changed again. In 2021, researchers studying Voyager data reported another clue that almost sounds small until you understand what it meant. They found a persistent background hum in the plasma beyond the heliopause. Not a one-time burst, not a rare event tied to a solar shock, a continuous signal. That mattered because it gave scientists a way to keep tracking plasma density more continuously. Density means how much stuff is packed into a given space. And what they found was not a smooth, unchanging environment. The density shifted. It fluctuated over distances of about 1 astronomical unit. That suggested turbulence. Turbulence is messy, swirling disorder in a flow. So now the picture got even stranger. The region around our solar system was not only being affected by the sun from the inside, it also seemed to be shaped by larger motions in the galaxy itself. The bubble around our home was sitting inside a restless neighborhood. Scientists gave this nearby interstellar region a more specific name, the Very Local Interstellar Medium, or VLISM. That means the thin zone of interstellar space immediately around our heliosphere, not the wider galaxy far beyond. And Voyager 1 was not drifting through a simple waiting room on the way to some perfect, untouched void. It was moving through the VLISM, a real place, a structured place, a place with history written into it. Now here's the second big twist. The most talked about puzzle in recent years began in 2020. At the time, Voyager 1 was about 149.3 astronomical units from the sun. Then its magnetometer recorded an abrupt jump in magnetic field strength. A magnetometer is an instrument that measures magnetic fields. The field rose fast. The plasma density rose too. Scientists call this event the second pressure front, or PF2. That by itself was interesting, but what came next was the real shock. Instead of the field simply rising and then settling back the way earlier events had done, it kept climbing, month after month. The magnetic field grew stronger and stayed elevated. It reached a peak in 2021 and then declined only slowly, remaining stronger than before. This strange long-lived structure became known as the magnetic hump. Even the name sounds mysterious, because it was. Voyager 1 had entered a prolonged region of enhanced magnetic field that lasted roughly from 2020 into 2022, while the spacecraft moved outward through more of the VLISM. Nobody writing old physics textbooks in the 1970s could have described that in detail. Nobody could have. There was no spacecraft there to see it, so this was not a case of scientists ignoring the answer. The answer simply had not been visible yet. Now jump to the new research. In 2026, fresh peer-reviewed work continued to examine this exact mystery. One major study used large computer simulations of how the solar wind and the local interstellar medium interact. Those simulations suggested that solar cycle-driven compressions hitting the heliopause could reproduce the puzzling magnetic hump Voyager 1 saw. In simple terms, the hump may have been caused by large-scale changes connected to our own sun, especially activity from solar cycle 24, arriving late and reshaping the medium outside the heliosphere. If that is true, it is astonishing, because it means the sun can still sculpt conditions in interstellar space tens of astronomical units beyond the heliopause, not by light alone, by pressure, by long-traveling compressions, by pulses that keep carrying force into the dark. That would make the heliopause feel less like the end of the solar system and more like a boundary across which the solar system keeps whispering. But here is the part they still have not fully resolved. After the magnetic hump, Voyager 1 entered a quieter region, and I do mean quieter. A 2026 study examining magnetic field observations from 2020 through mid-2025 reported that the behavior of the magnetic field after the hump looked very different from what came before. Earlier, the fluctuations were more jagged, more uneven, more turbulent. After the hump, they became smoother, more Gaussian, more calm. Gaussian is just a way of saying the variations look more like the familiar bell curve pattern expected from ordinary random behavior. That sounds technical. But the basic idea is simple. Before, the field looked wild. After, it looked strangely well behaved. That changes one of the biggest reasons this story matters right now. Because scientists are still debating what that calm actually means. One possibility is dramatic. Maybe Voyager 1 has moved into a truly different region, a part of the local interstellar medium less disturbed by the heliosphere, a zone closer to the pristine interstellar medium, meaning a cleaner sample of the galaxy beyond the sun's immediate influence. If that were true, the influence of our heliosphere on the surrounding region might extend much farther than the heliopause crossing alone makes it seem. That would be huge. It would mean the true transition from solar-shaped space to more undisturbed galactic space may happen farther out than the famous 2012 crossing suggested. But there's another explanation. And this is the third twist. The quieter post-hump region may not be a brand new realm at all. It may be a wake, a filtered zone left behind after the magnetic hump and related solar-driven disturbances weakened the earlier turbulence. In that idea, Voyager 1 is still in the VLISM, shaped by our heliosphere, just in a calmer phase created by the passage of earlier compressions. So the calm may be real, but it may not mean freedom from the sun. It may mean the opposite. It may be another fingerprint of the sun's long reach. That is why scientists are still debating it in current papers. Not because nobody has ideas, they do, but because the data can still be read in more than one way, and nature has not finished revealing the answer. This is one of those rare moments when you can feel science happening live. Not as a museum display, not as a settled chapter, but as a genuine argument unfolding in real time from a trickle of data sent by a spacecraft launched before many grandparents became adults. And if hidden stories like this are why you come here, subscribe now, because this is exactly the kind of frontier where the universe stops acting simple and starts telling the truth in fragments. There is also something deeply human about this story that numbers alone can hide. Voyager 1 is not a giant futuristic machine with endless power. Its main transmitter is about as powerful as a small household light bulb. By the time that signal crosses roughly 25 billion kilometers and reaches Earth, it is unimaginably faint. Yet the Deep Space Network can still hear it. The Deep Space Network is a global system of giant radio antennas. The biggest dishes are about 70 meters wide. They sit in places like California, Spain, and Australia, so Earth's rotation never completely cuts us off from deep space missions. Imagine needing an antenna the size of a building just to catch a whisper. That is what this mission has become, and the whisper is slow. The data rate from Voyager 1 is tiny compared with anything you use every day. Not movies, not music, not even a simple modern web page. Just a thin stream of bits, a trickle. And yet from that trickle comes the evidence behind debates in major scientific journals. That should humble all of us, because it means some of the most important things we know about the border of our cosmic home arrived almost one grain at a time. There's another reason the stakes feel so sharp. Voyager 1 is dying. Not dramatically, not all at once, slowly. It is powered by radioisotope thermoelectric generators, often called RTGs. These systems turn heat from decaying plutonium into electricity. They have been fading for decades. NASA says the spacecraft loses about 4 watts of power each year. That may not sound like much. But out there, every watt is life. Every watt is another instrument kept warm. Another measurement returned, another month of survival. Because of that decline, engineers have had to shut down instruments one by one. In February 2025, Voyager 1's cosmic ray subsystem was turned off to save power. On April 17, 2026, NASA shut down the Low Energy Charged Particles instrument as part of that same painful strategy. That left 2 key science instruments still operating on Voyager 1, the plasma wave system and the magnetometer. Look at the strange beauty of that. The very instruments still alive are the ones helping reveal the nature of the region around our solar system. The mission is being stripped down to its bare essentials, and yet those essentials are still enough to challenge our picture of the cosmos. NASA engineers are even testing a more ambitious power-saving plan nicknamed the Big Bang. The idea is to switch groups of devices and use lower power options where possible, freeing enough electricity to keep the spacecraft scientifically alive longer. In 2026, that strategy was being tested on Voyager 2 first because it is closer and slightly safer to experiment with. If it works, a version of that fix can be tried on Voyager 1. Think about the tension in that sentence. A spacecraft from 1977 is now living on careful electrical surgery. And we are doing it because the place around our solar system is still hiding things. This is not nostalgia. It is not keeping an old machine alive because people feel sentimental. Voyager 1 is still useful right now. In fact, it is helping newer missions. One of them is IMAP, the Interstellar Mapping and Acceleration Probe. IMAP launched in 2025 and reached its operating region near the first Sun-Earth Lagrange point, called L1, in early 2026. L1 is a place in space where a spacecraft can maintain a useful position between Earth and the Sun. IMAP studies the heliosphere from the inside by analyzing particles that come from its boundary and from beyond. Those particles help scientists map the shape and behavior of our solar bubble. But there is a catch. To understand what those incoming particles really mean, scientists need to know what conditions are like on the outside of the heliosphere too. That is where Voyager 1 becomes priceless. Voyager 1 is the direct sampler, the witness already out there, the old explorer on the far side of the border. So a brand new mission near Earth and a nearly half-century-old spacecraft far beyond the planets are, in a sense, working together to decode the same frontier. That partnership is one of the most beautiful parts of this entire story. One machine studies the boundary from inside, one machine studies it from outside. Across a gulf of billions of kilometers, they help complete each other's view. If you ever want proof that science is a relay race across generations, this is it. And still, Voyager 1 keeps outrunning expectation. NASA says that on November 18, 2026, Voyager 1 will become the first human-made object to reach a distance of 1 light day from Earth. That means light itself, moving at the fastest speed the universe allows, needs a full 24 hours to cross the gap between the spacecraft and our planet. A 1-day conversation delay. A machine so far away that even light has to work for it. That should change the way you feel about the night sky. Because this is not happening in some abstract science fiction map. It is happening in the same universe where you breathe, sleep, worry, and love the people around you. And that brings us back to the question hiding underneath all of this: why should you care? Because the region Voyager 1 is exploring helps define the shield around our solar system. It affects how scientists think about cosmic rays. Cosmic rays are high-energy particles that move through space and can affect technology and biology. The heliosphere helps block part of that radiation. So when we learn how the VLISM presses on the heliosphere, disturbs it, and changes the boundary around it, we are learning something about the conditions that help protect life on Earth. Not in a movie way, not in a panic way. In the real, patient way science matters, the shape of our shield matters. Its surroundings matter. The long argument between the sun and the galaxy matters. And Voyager 1 is giving us our first direct clues about how that argument actually works. There is also a deeper emotional truth here. We grew up thinking the universe is divided into places with clear labels. Planet, space, interstellar space, outside, done. But nature does not respect our neat borders. The edge of our system is not a line drawn with a ruler. It is a zone of influence, a conversation, a struggle between outward and inward forces, between a star's breadth and the galaxy beyond it. That is why the story feels unsettling. Because it tells you that even the edge of home is more alive than you thought. It shifts. It reacts. It remembers. And if our own heliosphere is this complicated, what about the bubbles around other stars? What about the environments surrounding alien worlds? What kind of radiation reaches them? What kind of protection fails them? What kind of strange border weather shapes whether a planet can stay friendly to life? You see how one old spacecraft starts opening much bigger doors. This is never just about Voyager. It is about what a home system really is. It is about how stars carve out temporary shelters in a rough galaxy. It is about whether safety in the universe is ever simple. And here is the final, almost unbelievable part. Voyager 1 was built for a primary mission measured in a few years. Yet here we are, nearly half a century later, using its data to write new papers about a region science could only guess at when the spacecraft left Earth. That should tell you something important. Human beings do not always know what our greatest tools will become. Sometimes we build something for one purpose, then time reveals a deeper one. Voyager 1 was sent to tour planets. It became our first witness beyond the sun's protective bubble. It became a messenger from the threshold between home and the galaxy. It became proof that the universe still has hidden rooms. And right now, as you listen, it is still moving, still measuring, still sending back signs from a place that refuses to become ordinary. And maybe the most haunting part is how easy it is to miss what that really means. They are not dry. They are clues. They are the fingerprints left on the wall of the room just beyond our door. And in a place this far away, fingerprints are everything. Let's slow down and feel the timeline, because the timeline is what turns this from a cool fact into a real story. Almost 50 years. Think of all of human life packed into that stretch. Children became grandparents. Nations changed. Technologies were born and forgotten. Entire digital worlds rose up around us. And all the while, this single machine kept going farther, carrying on a conversation with Earth so slow that a full question and answer can take 2 days. There is something beautiful in that slowness. We live in a time that trains you to expect instant replies, instant maps, instant certainty. Voyager 1 gives you none of that. It teaches patience. It reminds you that some truths arrive late. Some frontiers reveal themselves only one delayed whisper at a time. And here's another piece people rarely stop to think about. Every command sent to Voyager 1 is a gamble with time. That means the people caring for Voyager 1 have to be calm, methodical, and brave. They are doing surgery by flashlight across interstellar distance. No drama music can improve on that. Reality already did. The mission also keeps exposing a truth about science that a lot of people never hear. Real discovery often does not look like a clean headline. It looks like competing explanations, each trying to survive contact with new evidence. One team says the post-hump calm suggests Voyager 1 may be entering a less disturbed region. Another says the calm can emerge naturally from solar-driven compressions and does not require a fundamentally new region at all. That tension is not weakness. That is science doing its job. Science is strongest when it resists easy endings, and the easy ending here would be tempting. You could say Voyager crossed the heliopause in 2012, entered interstellar space, and now everything after that is just bonus scenery. But the truth is richer. The truth is that the famous crossing was the beginning of a harder mystery, not the end of one. Because crossing into interstellar space did not answer what lies just outside our sun's influence. It opened the door to the question. That question matters for another reason too. Our solar system is not sitting still. The sun moves through the galaxy. The local interstellar environment around us has its own flow, pressure, and magnetic shape. So the heliosphere is not frozen like a glass ornament. It is more like a ship's bow wave moving through a larger sea. If that sea changes, the shape of our protective bubble can change too. If the magnetic conditions outside the bubble change, the ways particles enter and move around the boundary can change. And if that can happen here, it can happen around other stars as well. Which means Voyager 1 is not just teaching us about our own frontier, it is giving us a way to imagine the frontiers of countless other star systems. That matters for exoplanets. Exoplanets are planets orbiting other stars. When people ask whether an alien world might be friendly to life, they often think about water, temperature, and atmosphere. Those are important. But the surrounding space environment matters too. How intense is the radiation? How strong is the star's wind? How stable is the protective bubble around that system, if there is one? What kind of interstellar weather presses on it from outside? Voyager 1 cannot answer all of that, but it can teach us the right kind of humility. It can show us that the space between stars is not just background, it is an active player. And once you understand that, the whole search for life becomes more complicated and more interesting. That is not because it is magical. It is because human beings designed it with care, and then generations of engineers kept learning how to stretch that care farther than anyone imagined. When one system weakened, they found a workaround. When power dropped, they made hard choices. When a signal became faint, the deep space network listened harder. When the spacecraft glitched, they found ways to recover it. The mission survived, not because machines do miracles alone, but because people refused to stop translating the whisper.